First of all, what is a mode? When we talk about the modes a molecule has, what does that mean?
I remember in lecture they talk about how like it's a box where we could put in like thermal energy and store it.
Yeah, it's often useful to think of it as sort of like a container. And of course, it's not really a physical container, but it is certainly a way for a particle to have energy. So for instance, if you have just let's say you've got a particle in a gas, let's say helium gas. Helium is a noble gas, so it's going to be monoatomic. Let's say you just have one helium atom. It's far away from other helium atoms because in a gas, they're very spread out. How many different ways could this helium atom have energy?
It's only kinetic, right?
Yeah, it's all going to be kinetic energy. The particle is able to move freely in space, but it's got no potential energy because there's nothing else to interact with. So this would just have kinetic energy, specifically translational kinetic energy. And how many different ways can it have translational kinetic energy?
3.
Yeah, we would describe this as 3 translational kinetic energy modes because we're in a 3-dimensional universe. This is able to move around in 3 dimensions. So it can have kinetic energy related to its motion forward and backward, its motion side to side, and its motion up and down. That's 3 dimensions worth of motion, so that counts as 3 different ways to have kinetic energy. And of course, it could have, maybe it's moving along a diagonal, but any diagonal can be thought of as just a combination of some amount to the west, some amount to the south, some amount up, or some other combination of those 3. So we only really need to describe 3 translational modes because we have a 3-dimensional universe. On the other hand, if we were dealing with a hypothetical 2-dimensional universe, if it is only able to move in 2 dimensions, then it would only have 2 translational modes. Or if everything were confined to move along a single straight line only, then it would be 1 translational mode. But in a typical 3-dimensional universe, such as the one we live in, every single particle is going to have 3 translational kinetic energy modes. And one of the most important things about modes is that if you've got lots of particles, let's say each one of these has 3 modes, what should we assume about, I mean, if each one of these modes is a way for a particle to have energy, what should we assume about the energy each one of those modes has?
It'll be the same.
It'll be the same under what circumstances? What has to be true in order for it to be the same?
Same temperature?
Yeah, as long as everything's at the same temperature, that is thermal equilibrium, then every mode should be assumed to have the same amount of energy. And that's really an on average thing. It might be the case that like maybe one of these molecules is moving slightly faster and another one's moving slightly slower, or maybe some of them are moving more in the X direction than the Y direction. But on average, we should assume that all the modes have approximately the same amount of energy, as long as everything's at the same temperature. This is usually called the Equipartition Theorem. Equipartition just means evenly divided or equally divided. The equipartition theorem says that if the temperature is uniform in the sense of the same everywhere, that is, we're at thermal equilibrium, everything's at the same temperature, then the energy, specifically the thermal energy, is evenly distributed to all the modes. Or we usually say all available modes or all accessible modes. Because we only want to include modes that are actually possible. It might be the case that, for instance, maybe this is confined to only move in 2 dimensions. Then you wouldn't have 3 translational modes, you just have 2 translational modes per particle. So all of the available modes, all the modes that are actually active. This also means that it doesn't really matter whether these substances are in contact. If you've got 2 substances that are at the same temperature, even if they're different substances, even if they're far apart, as long as the substances are at the same temperature, then each mode has the same amount of energy. So another way of phrasing this equipartition theorem is that the energy per mode depends only on temperature. Energy per mode depends only on temperature. It doesn't matter what kind of mode it is, whether it's kinetic energy or potential energy or what. It doesn't matter what kind of particle it is, monoatomic, polyatomic. Doesn't matter what element or chemical it is, doesn't matter what phase it's in, doesn't matter what planet it's on. Whatever the substance is, the energy per mode depends only on the temperature. In the sense that the higher the temperature is, the more energy each mode has. And that's a direct linear proportionality. The thermal energy per mode is directly proportional to the temperature. In fact, it's very useful to think of temperature as meaning energy per mode. When we say this object's temperature has increased, we're really saying all of the modes now have more energy than they used to. And proportional in the sense that if the temperature, let's say the temperature is tripled, and that means this has to be in kelvins. So if the temperature in Kelvin triples, let's say from 100 Kelvin to 300 Kelvin, then the energy per mode also triples. Every mode has 3 times as much energy as it used to. Any questions on that so far?
So it's pretty much just each mode has it depends on how much modes.
In terms of the total thermal energy, yes. Every individual mode, like let's say we're looking at just the X direction kinetic energy, of this one atom. That's one mode, the kinetic energy in the X direction. And usually we don't think of energy as having a direction, but it's useful to split it up into coordinates in this case. If we think of just the kinetic energy along the X-axis, that mode has a certain amount of energy, and the amount of energy depends only on the temperature. It doesn't matter how many modes there are in the atom or molecule. It doesn't matter how many molecules there are. This one mode has energy that depends only on the temperature. But if you want to find the total energy of this atom or the total energy of some cluster of atoms, then you need to know how many modes there are, and then multiply that by the energy per mode. Any other questions on that so far? And to find the energy per mode, if we know 2 quantities are proportional, what does that tell us about how they're related to each other? How would you write an equation describing 2 quantities that are proportional?
Just equal or?
Yeah, equal with a constant multiplier as well. If we know energy is proportional to temperature, we can say energy equals something times temperature, some constant times temperature. And that constant has to do with how those are related in terms of converting one to the other. In fact, the coefficient here determined experimentally turns out to be half of another constant called Boltzmann's constant. So Boltzmann's constant divided by 2 is the conversion factor from temperature to energy per mode, which means what do the units of measurement have to be for Boltzmann's constant? What are the usual units for temperature? Yeah, energy is in joules, temperature is in kelvins. So Boltzmann's constant needs to be measured in joules per Kelvin so that kelvins cancel out and we introduce joules. So Boltzmann's constant is a number of joules per Kelvin. And it could be described in other units as well, but joules per Kelvin is the usual. And it's also an extremely small number because we're talking about energy at the atomic level. One mode is just some part of an atom in terms of part of the energy that atom has. So Boltzmann's constant is absurdly small, somewhere around the order of, I think, 10 to the negative 21st or something like that. Very small numbers because we're dealing with individual atoms. But the idea is this allows us to calculate how much energy each mode has. And most importantly, this means that at the same temperature, energy per mode is consistent, no matter what type of particle it is, no matter what type of mode it is. So if we were dealing with, let's say instead of having just one helium atom, let's say we had a cloud of helium gas that was let's say 5 moles of helium gas. And let's say we know the temperature. Let's say the temperature is 400 Kelvin. We could use this idea to construct a formula for thermal energy of this sample. If we want the thermal energy, we know that the thermal energy of one mode is Boltzmann's constant over 2 times the temperature. So this is the energy of one mode. But how would we scale that up to energy of one atom? And let me go ahead and fill in the temperature, since we know this temperature happens to be 400 Kelvin. How would we scale that up to the energy of the entire helium atom?
It's just one atom, so, or five moles times Avogadro's number.
Well, not the whole sample yet, just one single atom. If one, not Avogadro's number yet, because we're not dealing with a whole mole, just one single atom. How many modes are in that one single atom?
3.
3. And we know that each one of those modes has this much energy. So how do we convert the energy for one mode into the energy for one atom? Divide by 3, so one atom will have 1/3 that much energy?
Multiply by 3.
Yeah, we should multiply this by 3. So the energy per mode times 3 tells you the energy of 3 modes, which is the whole atom. So that means this energy is for one atom. That is, one helium atom will have 3 times Boltzmann's constant over 2 times 400 kelvins as the energy of that one atom. And this is still going to be absurdly small because Boltzmann's constant is a very small number, and we're looking at the energy of one single atom. Of course, we're not dealing with just one single atom. We're dealing with 5 moles of atoms. So how do we scale up from energy of one atom to energy of the whole sample?
Do you now multiply by 5?
Yeah, multiply by, and not just 5, because it's not just 5 atoms, it's 5 moles of atoms. So how many atoms would that be?
Avogadro's number.
Yeah, 5 times Avogadro's number. So we're taking the energy of one atom and multiplying it by the number of atoms, which is 5 moles. So that means this whole thing is now the energy of the whole sample. We can say thermal energy, and this is thermal energy because it depends on temperature. It's also the kinetic energy of the individual molecule, the individual atoms. So in this case, the thermal energy of the whole sample is the kinetic energy of all the atoms combined. That's really what thermal energy is. Thermal energy is the kinetic energy, and in some cases, potential energy as well, of the individual microscopic particles. But if we multiply all this out, that should tell us the thermal energy of the whole sample. So we've got half of 400 is 200, times 3 is 600, times 5 is 3,000. So 3,000 kelvins times Boltzmann's constant times Avogadro's number. And this is going to be in joules per Kelvin, so the kelvins and kelvins will cancel out. We could fill in the very, very small Boltzmann's constant and the very, very large Avogadro's number. But there's a shortcut here. Boltzmann's constant, very, very small, and Avogadro's number, very, very large, show up together frequently enough that they have their own abbreviation. The very, very small Boltzmann's constant times the very, very large Avogadro's number works out to a much more convenient number, about 8.3 joules per Kelvin, and we call that R. And this is, it turns out, the same R you see in the ideal gas equation. This is the ideal gas constant. I think it's about 8.31 joules per Kelvin. or sometimes written as joules per Kelvin mole. In the sense that if you think of this 5 as being written as 5 moles, we want moles and moles to cancel out. Technically, moles is unitless because moles isn't a unit of measurement. It's not like a distance or something. Mole just means 600 septillion. That is Avogadro's number of the things. But if we replace KB times NA with R, this is much easier to calculate. We don't need to multiply very, very small number times very, very large number every single time. We can just say this is 3000 kelvins times about 8.31 joules per Kelvin. So that's going to be 24,000 and another 900-ish. So about 24,930. Let's say about 24.9 kilojoules. So that would be the thermal energy of this cloud of 5 moles of hot helium gas, about 25 kilojoules. And note that we did all this without looking up any specific heats on a data table. We can figure out the thermal energy just based on how many modes the particles have combined with how many particles there are. So this allows us to bypass the need for looking up information about specific heat. We can base the whole idea just on the behavior of the individual particles. Any questions on that so far? Or let's try out another example. Let's say instead of helium gas, let's say we have liquid helium. So it's still monoatomic since it's still a noble gas. But in liquid form, what's going to be the biggest difference here? What's the main difference between liquid versus gas as far as the individual atoms goes?
They have potential energy.
Yeah, they're going to have potential energy because in a liquid, they're going to be much closer together. In a gas, we assume the particles are so far apart that they're not interacting in a meaningful way. But in a liquid, the particles are much closer together. Not perhaps as tightly packed as they would be in a solid, but close enough that they're at least interacting. And in fact, whether it's a solid or liquid, we're going to treat it the same way. The particles are interacting with each other. Are they still able to move?
Yes.
Yeah, even in a solid, they're on average staying still, but they are vibrating in place. So that does count as movement. In a liquid, they're sort of swirling around, they're just staying close to each other. So that also counts as movement. But whether it's a solid, liquid, or gas, the particles can still move in 3 dimensions. So we still have 3 kinetic energy modes, and this is per particle. Each atom here has 3 kinetic energy modes because it's able to move in 3 dimensions, even if it's not moving very far. And also it's interacting with its neighbors. If it's interacting with its neighbors, that's potential energy. And how many dimensions can it interact with its neighbors in?
3.
Yeah, so we'd have 3 potential energy modes per particle also. This particle can interact with its neighbors to the north and south, can interact with its neighbors to the west and east, and can interact with its neighbors above and below. That's 3 dimensions worth of interaction. So that means we have 3 potential energy modes for each particle. And note that these are not the same as bonds. This has nothing to do with how many bonds there are in terms of what we were looking at for bond energy. The 3 here is all about dimensionality, the fact that this exists in a 3-dimensional universe. So it has 3 dimensions worth of interaction and 3 dimensions worth of motion. Each one of those can have a certain amount of energy, specifically half of Boltzmann's constant times the temperature. So if we wanted to know the thermal energy of, let's say, 5 moles of liquid helium at a certain temperature, we could do the same sort of process. We still have half of Boltzmann's constant times the temperature, which would probably be lower because helium is not going to be liquid at this high of a temperature. Instead of multiplying by 3, we'd multiply by 6 because there's 6 modes altogether per particle, and then multiply by the number of particles. So still the same basic procedure, we'd just be having a different number of modes. Any questions on that so far? And a couple more quick examples. Let's take a look at what would happen if we had a more complicated particle. Instead of monoatomic, let's say we have a diatomic gas, like nitrogen or oxygen. And they're all going to behave the same. And for any diatomic gas, we've got a pair of atoms that are bonded together. And that pair of atoms, since we're treating this molecule as one unified object, we're assuming they're not leaving each other. So this one molecule is still able to move in 3 dimensions. So it's still got 3 translational kinetic energy modes. Can this interact with other particles nearby?
Yes. Or non-gas, no.
Right, in a gas, it can't interact with other particles because there are no other particles nearby. Let's say the next nitrogen atom is going to be maybe way over here. And then maybe there's one down here. Since these are so far apart, they are effectively not interacting with each other at all. So that means we could ignore their interaction. Maybe they are presumably still attracting very, very slightly based on the Lennard-Jones potential energy graph, but so little we can ignore it. So we assume that the interactions here has no potential energy associated with it. So we don't need to include that. But how else could this molecule have energy that we now need to consider? It can have kinetic energy by virtue of moving around. How else could it have kinetic energy if it's not just a single atom?
There's potential energy maybe in the bond.
Yeah, there could be potential energy within the bond because that bond is not just a solid, rigid object. Those 2 atoms could be vibrating against each other inside the molecule. We often call that internal vibrational energy. So internal vibrational modes. And along that bond, how many dimensions is the oscillation along the bond? If we consider the motion of the individual atoms inside the molecule.
Is it just 1?
Yeah, it counts as just 1-dimensional. Because within this molecule, the atoms could be vibrating towards each other or away from each other. That's just 1 dimension. You could also consider, for instance, what if they're both moving upwards? But if they're both moving upwards, that's just a translational mode. Or maybe one's moving up and the other's moving down. But if one's moving up and the other is moving down, what's the molecule actually doing?
Rotating.
Yeah, if one's moving up and the other's moving down, that's not really a vibration, that's a rotation. And we generally include that also as rotational kinetic energy. So this molecule could be moving around, changing its position in space. It could be spinning, that counts as rotational kinetic energy. Presumably it's doing both at the same time. It's moving and spinning. And also within the molecule, there could be vibration of the atoms along that bond. For rotational modes, and we'll come back to internal vibrational modes in a moment. For rotational modes, how many dimensions of axis could this rotate around?
Would it be 2?
And why only 2 instead of 3, given that we're in a 3-dimensional universe?
Because when it's like rotating in place, it doesn't we don't really count it as 1.
Yeah, for any object that's able to rotate, you could rotate around the z-axis like this. You could rotate around the x-axis like this. If you rotate it around the y-axis, in this case, rotating around its own axis of symmetry, nothing's really changing. This does not count as a rotation we care about because the individual atoms don't really move if you spin like this. So the axis of its own symmetry does not count as a rotational mode. So this will only have 2 rotational kinetic energy modes. What would have to be true in order to have 3 rotational modes, for all 3 rotational modes to be active?
It's nonlinear.
Yeah, it would have to be nonlinear in shape. You can't really get this with something that's linear in shape that has rotational symmetry. But if you got something nonlinear, like let's say a pair of pliers, for instance, this pair of pliers, if I rotate around this axis, that counts as rotation. If I rotate around this axis, that counts as rotation. And if I rotate around, did I do this one already? This one, this one, this one. So we've got this rotation, and this rotation. That's 3 different axes of rotation that all count as separate rotational modes. So if the shape is nonlinear, if you have even a single bend in it, then that counts as 3 rotational modes. But if all the atoms in the molecule are arranged on a straight line, no matter what the size is, no matter how many different atoms you're looking at, if they're all arranged in a straight line, that still has only 2 rotational modes. But if there's even a single atom that's off of that line, that now becomes 3 rotational modes, because that makes it no longer rotationally symmetric. So generally for rotational modes, you'd have either 2 if it's linear in shape, which includes every diatomic molecule, or 3 if it's nonlinear in shape, if there's anything off of that central axis. And then for monoatomic, you would have no rotational modes at all because a single perfect sphere can't rotate in a meaningful way. So for this one, diatomic, you're always going to have the 3 translational modes. You could have 2 rotational modes, unless it's too cold. It turns out that the rotational modes require a certain amount of energy to be active in the first place. This isn't like a macroscopic object. Like for a macroscopic object hanging from a string or something, you tap it, it's going to rotate. You bring it to a stop, tap it softer, what would you expect to happen? Like if you know you have this object hanging from a string, you can tap it to make it rotate. If you instead tap it more softly, what would you expect to happen there?
Less rotation.
Sorry, what was that?
Less rotation?
Yeah, it's still going to rotate. It's just going to rotate more slowly. And then tap it even softer, it's going to rotate very slowly. However, it turns out that at the molecular level, that doesn't really happen. There's a certain minimum amount of energy that can get it to spin. Less energy doesn't mean it will spin slower. It means it won't spin at all. So you wouldn't have the rotational modes. So there's a certain minimum threshold amount of energy to be rotating in the first place. Less energy means it doesn't rotate at all. And what does the energy per mode depend on?
Temperature.
Right, it's all about temperature. So if the temperature is too cold, then there's not enough energy per mode to allow this to rotate. So the rotational modes would not be available. We would say those modes are frozen out, and it would only have the translational modes. And there's not really a hard limit as to when modes are frozen out versus when they're active. For diatomic gases, though, the general rule of thumb I've seen is that if you're at about room temperature, we'd assume the translational modes and rotational modes are active, but the vibrational modes are frozen out because the vibrational modes also require a certain minimum energy to activate. At room temperature, we'd assume internal vibrational modes are frozen out, so it would have 5 modes. At very cold temperatures, like way below room temperature, rotational modes are also frozen out, so this would only have the 3 translational modes and that's it. At very hot temperatures, they would all be active because there would be enough energy to make all of these happen. So that's when we use the term frozen out. When we say modes are frozen out, that means it's too cold, too low of a temperature to have enough energy to activate those modes. And that's what the equipartition theorem was getting into in terms of accessible modes. We only count the modes that are actually active, not the ones that are frozen out. This also means that as you gradually raise the temperature of an object, you may unlock more and more modes. If there are some modes that were frozen out, but you raise the temperature, there may now be more modes per particle and even more as the temperature increases. Any questions on that so far? So let's get back to the internal vibrational modes. We know that it's only vibrating in one dimension. Within the molecule, we only have one dimension of vibration. Because you can treat this, this bond as if it were a tiny invisible spring. But along that one dimension, what kinds of energy do the particles have? If you imagine you have two tiny objects attached by a spring and they're oscillating, what kinds of energy do they have?
Spring mass.
Yeah, spring mass, potential energy, and also because they're in motion, they also have what else?
Vibration.
Sorry, what was that?
Vibration.
Well, what kind of energy is that? If you've got an object in motion, what kind of energy is associated with that?
Kinetic.
Yeah, kinetic energy. So if we treat this as a tiny invisible spring, there's spring potential energy, although it's actually Lennard-Jones potential energy, but it acts a little bit like a spring. So potential energy from the fact that they're interacting in one dimension. And also kinetic energy in the sense that they're able to move in that one dimension. So the internal vibrational modes would actually be two, of which one is kinetic and one is potential. In fact, in general, the internal vibrational modes come in pairs. They have to have some number of kinetic energy and the same number of potential energy. So this is always going to be an even number of internal vibrational modes, because every kinetic energy is matched by potential energy when you're talking about vibrations. Any questions on that so far? So it looks like this will have as many as 7 modes if they're all active, if you're at a very high temperature. If you're at about room temperature, I would expect the internal vibrational modes to be frozen out, so we'd only have 5. At even colder temperatures, I would expect possibly as little as 3. But at least 3, no more than 7 for this diatomic molecule. Any questions on that so far? Then let's see if we can deal with a larger molecule. If we have a longer molecule, let's say it's still linear, but a long linear molecule with, let's say, n atoms. So we've got possibly a very long molecule. We don't know how many atoms, but let's just use n for the number of atoms. If we want to list out all the modes it has, what should we start with?
The amount of energy per mode.
Well, not the temperature. I mean, we can use that to find the total energy. But if we just want to count up how many modes, because the energy of the molecule will be energy per mode times number of modes. But if we want to use that, we'll first have to figure out how many modes we're dealing with. And no matter what kind of molecule it is, what modes can we always include?
Translation.
Yeah, this long molecule is definitely going to have 3 translational modes. 3 translational kinetic energy modes. And also, assuming the temperature is warm enough for them to be active, it could also have rotational modes. And how many of those would we expect?
2.
Yeah, since it's linear, we'd expect 2 rotational kinetic energy modes. And let's say this is in a gaseous phase, so we don't need to worry about interaction with other molecules because they're too far apart. And then for the internal vibrational modes, at this point, this is going to be too complicated to count up by hand because these could be interacting with each other, these could be interacting, these could be interacting, these could be interacting, any pair of these could be interacting. And it gets very complicated to try and count those up by hand. But one thing we can do here is predict how many ways they can interact by looking at the atoms individually. So if we consider the individual atoms here, if you just look at any one individual atom, how many kinetic energy modes would you expect that one atom to have?
Five.
Sorry, what was that?
5.
Can this move in 5 dimensions?
Or 3, sorry.
Yeah, if we've got a single atom, we can expect it to have 3 translational modes. Because this one atom, ignoring everything else around it, this one atom is able to move in 3 dimensions, the x direction, the y direction, and the z direction. So we should expect each atom to have 3 kinetic energy modes. Each atom should have 3 kinetic energy modes. And if we have n atoms, how many kinetic energy modes should we expect altogether?
3n.
Yeah, 3 times n would be the total number of kinetic energy modes we should expect. So we expect 3n kinetic energy modes in total for the whole molecule. But based on the analysis of the whole molecule, how many kinetic energy modes have we actually counted so far? Yeah, so far we've counted 5 kinetic energy modes. We've got the whole molecule could be in motion, that's 3 translational modes. The whole molecule could be rotating, that's 2 rotational modes because it's linear. So far we have counted 5 modes of the 3n modes we expect. But that means we haven't counted all of them. N might be very large, like maybe n is 100. If there's 100 atoms here, we would expect 300 kinetic energy modes. We've only counted 5 of them, so how many are remaining to be counted?
Would it be 2, the rotational ones?
Well, how many modes are we expecting here? Because we already counted the 2 rotational modes. In total, how many modes are we expecting for the whole molecule?
5?
Well, we've already counted 5 kinetic energy modes, but based on the behavior of the individual atoms, how many kinetic energy modes in total should we expect?
6.
Not just 6. Let's say this is 100 atoms. How many kinetic energy modes would you expect 100 atoms to have?
6 times the number of atoms.
Yeah, well, 3 times the number of atoms, because each individual atom has 3 modes, 3 kinetic energy modes. If each individual atom has 3 kinetic energy modes, because it can move in 3 dimensions, we should expect 100 atoms to have 300 kinetic energy modes. So the whole molecule, if it's got 100 atoms, the whole molecule should have 300 kinetic energy modes. But we've only accounted for 5 of them. How many are left over that are still mysterious that we haven't counted yet?
Isn't it the vibration one?
It should be the vibrational modes. So how many are left over? If we expect 3n, and we've already counted 5 of them, how many are left uncounted?
295.
Yeah, if we've got 100, if we expect 300 modes, but we've only counted 5, there are still 295 mysterious modes we haven't counted yet. And how did you get that number? How did you get that 295?
Subtracting by the total kinetic modes.
Yeah.
With what we counted.
So in general, if we're expecting 3n kinetic energy modes, where n is the number of atoms, and we've only counted 5 of them, there are 3n minus 5 leftover modes that we haven't counted yet. So we should expect 3n minus 5 mysterious modes that are presumably going to be the internal vibration. (3n minus 5) other kinetic energy modes unaccounted for. And those are exactly the internal vibrational modes. But that's only the kinetic energy by internal vibrational modes. If we've got a certain number of kinetic energy internal vibrational modes, what else do we need to include?
The string mass?
Yeah, in other words, the potential energy. We've got this many kinetic energy modes associated with vibration. We should have the same amount of potential energy modes associated with vibration. So we're going to have to double this because this is only the kinetic energy of vibration. We also have that many more potential energy. If you double this, what do you get?
Um, 295 multiplied 2.
Or if it's 3n minus 5, what do you get if you multiply this by 2? Yeah, 3n doubled becomes 6n, minus 5 doubled becomes minus 10. So this turns into 6n minus 10 as the internal vibrational modes. And that includes kinetic and potential. From our analysis of the individual atoms, we found that we should expect 3n kinetic energy modes altogether. We already counted 5 of them, so there are 3n minus 5 other modes, which turn out to be the internal vibrational kinetic modes. But we also have the same number of potential modes associated with it because they come in pairs. So 6n minus 10 would be the total number of internal vibrational modes for this enormous molecule. And then if we add those all up, we've got 6n minus 10 plus the 5 we already accounted for. So what's the total there?
6n minus 5.
Yeah, 6n minus 5 modes. And so this should be true for any linear molecule in gas phase. If you've got any linear molecule, no matter what size it is, as long as all the atoms are arranged in a straight line and it's in a gas phase, the total number of modes per molecule should be 6n minus 5. For example, with that hypothetical 100 atom molecule, if you got 100 atoms, you'd use 100 for n. So 600 minus 5 would be 595 modes. That's assuming they're all active. So none of them are frozen out. So that would only be at very high temperatures. Or we could also test this out with what n value have we already analyzed in detail? What molecule were we just looking at where we could count up everything by hand?
Monoatomic.
Monoatomic, the problem is this doesn't really work for monoatomic because we were assuming from the start that it has 3 translational and 2 rotational. Monoatomic wouldn't have the 2 rotational. So this doesn't really work for monoatomic. So one step further than that.
The diatomic?
Yeah, if we try applying this to diatomic, what did we find earlier for the total number of modes per particle for a diatomic gas?
It was 7, or?
You should expect at least, well, at most 7 anyway, assuming they're all active. If we try applying this formula for diatomic, what would n equal? How many atoms are in a diatomic molecule? Yeah, n equals 2. So if you plug in 2 for n, 6 times 2 minus 5 gives you what value? If we fill in 2 for n, what do you get there? Yeah, 6 times 2 is 12, minus 5 is 7. So this formula works for the example we already tried. This formula, and not just for that one, but for any number of atoms. As long as you've got a linear molecule with n atoms, 6n minus 5 should tell you the total number of modes to expect if they're all active. It might be fewer than that at low temperatures. Some of them might be frozen out, but this tells you the hypothetical maximum, assuming they're all active. And that works for any linear molecule. If it's nonlinear, what would we have to do differently? What's going to be different in our analysis if it's nonlinear? Like if there's some that are off of that line? What would be the biggest difference in the startup?
There would be more rotational kinetic energy.
Right. If it's nonlinear, then instead of having 2 rotational modes, we'd have 3 rotational modes, which means instead of counting 5 kinetic energy modes, we'd count 6 kinetic energy modes. We'd still expect 3n total, but we've already counted 6. So instead of having 3n minus 5 left over, we'd have 3n minus 6 left over. Double that, we get 6n minus 12. And if we add those up, 6n minus 12 plus the 6 we've already counted, how many do we have in total?
6n minus 6.
Yeah, 6n minus 6 modes. So we'd use that formula if it's a nonlinear molecule. But this now allows us to predict the number of modes to expect for any size molecule, as long as it's larger than monoatomic, regardless of whether it's linear or nonlinear. You just use different formulas depending on what shape it is. So 6n minus 5 if the molecule is linear in shape, 6n minus 6 if it's nonlinear. And that'll allow you to quickly predict the total number of modes to expect for that molecule. Just keep in mind that at low temperatures, those internal vibrational modes are going to be frozen out. So you'd only have the 6 or 5. And at very low temperatures, the rotational modes could also be frozen out. So you might just have the 3 translational modes and that's it. So pay attention to the temperature and look at how many modes you would expect to be active. Any other questions on that? All right, then I will see you next time.